Hello students, welcome to the series of lectures on digital speech processing. So in this video I am going to explain the classroom discussion topic of excitation of sound in the vocal tract. So in the previous video we have seen what is the speech signal introduction and how the process of speech production that can be possible. Now in this video today we are going to be concentrating on the excitation of sound in the vocal tract. Okay, so let's get started. So this is the lecture learning outcome. So on completion of this lecture, you will be able to understand the sound generation through the vocal tract. So this is the signal processing hierarchy that we already know. So for our purpose of main course is that signal representation and then signal transformation. So that put together we are calling it the signal processing. So this is the schematic view of the vocal tract. Just recall in the previous video also we clearly seen this. So as the air is released from the lungs via the trachea or the windpipe, so the tensed vocal cords within the larynx are caused to vibrate by the airflow. Okay, so that way how the sound is going to be coming from through the lungs to the vocal cord and then through the lips. Okay, so this is the schematic also we have seen. So how the air is flowing from the lungs to the vocal cords and then vocal tract. Now we are in this video we will be interesting towards the sound excitation from the vocal cords, how the sound is going to be generating in the vocal tract. Okay, now we are going to be designing a model in such a way that it has to suit the structure of the vocal tract, how that is already we have there in the parameters, and how the signal that is coming from the vocal cords, the same signal is going to be listened by the listener. So as we clearly mentioned in the previous video also, so the vocal cord is in closed position, then whatever the air that is coming from the lungs, okay, so will not be flows towards the vocal cords here. Okay, and we can also examine one important point that so this vocal cord is nothing but the mechanical oscillator. Okay, because it is closed and after some time it is open, close, close, open, open, close, like this. So this is the way that is going to be happening. Okay, and if you want to see the pictorial representation of that oscillator, it should be like this. Okay, so this is the best example, the glottal flow we can call it. Glottal flow is nothing but the vocal cords only. So this is an air flow. We have given the pictorial representation in the time domain. Okay, this is the time axis and this is the air flow. Okay, so if the vocal cords are open, then the air is going to be flows from the lungs to the vocal cord through the vocal tract. Okay, so that way you need to understand. So this is the region actually. This is the portion where the airflow will be maximum. The vocal cords is also open now at that point of time, and there will be a sound that is coming through the lips. Okay, and similarly this is the closed phase. Okay, as the vocal cord is in closed position, then there is no airflow at all. So like that you need to understand when you look into this pictorial representation. Okay, and here. And we need to estimate the period. Either you take the two peaks, okay, whether the vocal cord is open, okay, and 2 times it is open, and we are estimating the period. Or you can also take the closed phases. Okay, either whatever you take. If you take the 2 upper positions of the airflow or the 2 lower positions of the airflow, that way we are calculating or estimating the period. Okay. And the below figure is that is a differentiated flow. Okay, so which is exactly the differentiation of the previous the above figure that we are seeing from the slide. Okay, so this way you need to understand. And here we can also estimate MFDR, that is the maximum flow declination rate. MFDR stands for maximum flow declination rate. So that way also we can easily, there is a threshold, and how that is going to be happening, we can easily identify that by looking into this pictorial representation. And this is an abstraction of the physical model, and this also we clearly seen in the previous video. the time varying filter. So this time varying filter is nothing but your vocal tract parameters. Okay, whatever the specification that we are going to be considering for the time varying filter, that are nothing but the vocal tract. And there is an excitation and the speech. And speech is a sequence of ever-changing sounds. We also know about all these things. This is a brief introduction which are related to the speech signal. And the speech waveforms also be clearly seen in the previous video. That is three important identification we can easily get from the signal. That is silence, voice, and then unvoiced. Right. So this is a system model for a speech signal. This is very important. How the sound is generated from the vocal cord, and how the sound is travels through the vocal tract, and the way how that is coming from the lips. Okay, so this is a complete model we can call. Okay, so this is an excitation generator, nothing but the vocal cords. So excitation parameter, it could be pitch, or it could be voice signal, or it could be unvoiced, or it is a hybrid mode. There's a mixed mode, voice and unvoiced. And this excitation signal is, I am calling as a voice and unvoiced signal. It is a mixed of voice and unvoiced. So that we can represent in a signal form like an impulse. Please understand, this is very important point I'm telling. So at the output of the excitation generator, whatever the signal that will be there here, so which is a voice signal and then unvoiced signal. So it is a mixed signal we can call, that we are going to be representing in the time domain as an impulse. Okay. So you can easily identify from this here is that, so this is a voice signal, there is an impulse, and this there is no impulse, that is an unvoiced signal. And similarly, this is voice, this is unvoiced. So like that we can easily estimate from the impulse. So that way we need to analyze the mixed signal, voice and unvoiced. It's just like a representation of the impulse. That can be given to the linear system. So where in the linear system the vocal tract parameters will be there. Okay. So it's just like a system of a filter. Whatever the filter that you want to design or a model, it could be analog filter, it could be the digital filter. So mainly we are applying the digital models to the speech signal. That linear system could be the digital filter. Okay, whatever the specifications, whatever we are going to be giving. So that specification is multiplied with the impulse signal is equivalent to the speech signal that we are going to see. Okay, so at the output of the linear system, we can have the speech signal like this. Okay, it is a combination of both voice and then unvoiced signal, right? And some of the three important points also I clearly mentioned below the figure. The discrete time varying linear system on the right of the figure, which simulates the frequency shaping of the vocal tract tube. Okay, so this is a vocal tract tube. The frequency, it simulates the frequency shaping, and this could be different, the words that you are speaking. Okay, and similarly, the second point, the excitation generator on the left of the figure, which simulates the different modes of the sound generation in the vocal tract. Okay, so how many number of sounds that they are going to be generating, that can be possible through the vocal tract itself. Okay, that we can see clearly seen from the point number 2. And I also mentioned the point number 3 in the slide is that the samples of the speech signals which are assumed to be the output of the time varying linear system. So these are the 3 very important points which are related to the figure that you are seeing. And in general, we can call this kind of model is a source system model of the speech production. Okay, so the way how we are generating the signal from the vocal cords, the way how the signal that is traveling through the vocal tract, and the way how we are getting the speech signal through the lips. So these are the 3 important points we need to remember. Okay, so as an example, this is a complete model we can easily witness. The excitation generator is a block, and the linear system, and the way how we are getting the signal at the output of the system. So more commonly to characterize the discrete time linear system, this is the function actually we are using. So H object, and we'll be having the poles and zeros. It is a ratio of the transfer function. So where the filter coefficients, which are changes at a rate on the order of the time per second that we can give. Okay. So mainly whatever the filter coefficients we have mentioned in this transfer function, which are labeled as a vocal tract parameters in the figure that we have clearly seen in the previous slide. Okay. So some of the poles of the system function lie close to the unit circle and which create the resonance to the model, the format frequencies. Okay, so format is nothing but it is a resonance actually, the vibration. Whenever the air is coming from the lungs to the through the vocal cords, there is a resonance and the sound will come. So like that we need to understand. So this is the slide. Actually, we can focus on the acoustics of a male and female vowels, which differ reliably along the two different dimensions, the sound source and the sound filter. The sound source is nothing but F0 actually, the source. So the fundamental frequency we need to calculate after seeing the speech signal perceptually. So which depends upon the length of the vocal folds. Okay, and this length of the vocal folds will be shorter for the woman. That is shorter in women, we can call the higher average fundamental frequency. Okay, there is an inversely proportional to each other. And similarly, so for men, the vocal chord length should be the more, and obviously the fundamental frequency will be less. Okay, and the formats is also similarly we can easily identify for different cases of the women and men. Okay, so for shorter in women, the higher format frequencies that can be possible. For longer in men, lower format frequency that can be possible. Okay, so this way we need to remember. Thank you, students. Thank you for watching this video.